Hello everyone. So we are discussing another topic today, that is electric power. Now the power is a term familiar to you. We have talked about this before in the previous semester under mechanics. Uh, Power is the amount of energy produced in a unit time. So if a machine producing mechanical energy like an engine moving a vehicle, like the engine inside a car, that creates mechanical energy that rotates the wheel, that moves the car. So the energy measured in joules and the amount of energy per a time interval, energy divided by time, is called power. So it could be the same amount of energy that is produced, but if you compare two machines, one produces 100 joules in 10 seconds, the other one produces 100 joules in 5 seconds. The second one, we say that it's more powerful. The power is higher, means it can produce energy faster. So when it comes to electricity, the amount of energy produced, electrical energy produced in a given time, so energy divided by time is defined as electric power. So power, we use the letter symbol P, capital P, is the amount of energy divided by the time interval. So this is energy measured in joules, time is in seconds, so it's joules per seconds, that's the unit of power. This is also called watts, and denoted by letter capital W. So when it comes to electricity, now power can be related to anything: heat energy, mechanical energy, kinetic energy. There's so many different types, right? But when it comes to electricity, we have unique equations using terms that are unique to electricity, like current, voltage, and resistance, and we can easily define power using those. How to get to that, we don't need to worry about that, how to derive these equations. But very useful, one of the very useful equation is power given as voltage times current. Over here the slide it's written as IV, and I prefer to write it as VI. So power is voltage times current. So if you have, let's say there's a circuit, there's a battery, voltage V, there's a resistor, some resistance R, and there's a current flow I. So let's say this resistance is some electrical equipment. It could be a light bulb emitting light. It could be an electric heater emitting heat energy, or some kind of machine that rotates like a household blender or something, a microwave. It could be anything. So the amount of joule it releases, the amount of energy it releases per time, is given as the power output of the device. So to find the power, we simply multiply voltage and current. So for this resistor, we know that the voltage across this is same as the battery voltage. So whatever the voltage across the equipment multiplied by the current through it, you get the power. So not just this P equals VI, there are two more equations we can derive using this. Let's go to the next slides. So if it is an ohmic device, remember we talked about Ohm's law some time ago, and things that obey the Ohm's law are called ohmic conductors, ohmic resistors, or ohmic devices in general. So we can replace, we know that V equals IR. So we can replace this V with this thing. So we get power equals IR times I, or I squared R. So here's another way of calculating power using current and resistance without voltage. Same thing, if you look at the slide, we replace current with V over R, then we get power equals V squared over R. So depending on the situation, you can use one of these. You don't have to use the first one all the time. If current and resistance given, you use the second one. If voltage and resistance given, use the third one, right? Okay, so this is how we find power, the energy output per time, how fast the energy is being produced. Bigger the power number, that means it's producing more energy per second. So if you are running, let's say if you are running two machines at home, a light bulb says 100 watts, right? You probably have noticed this. When you buy light bulbs, you look for this particular number. Some say 75 watts, some say 60 watts. So if you need more light in the room, you will go with a bigger power number, right? That means it emits more energy per time. That's the idea of power. Microwave ovens typically says 1000 watts, and if you look at heating instructions for certain frozen food, they say, okay, in a 1000-watt microwave oven, put it for like 3 minutes. The idea is you need to know how much energy you get per second, and that determines, the cooking time and all that. So let's go to the next slide. Let's try some examples. Alright, here's an example. Headlights from maybe a car. Calculate the resistance of a 40-watt automobile headlight designed for 12 volts. Okay, so if I draw this situation in a circuit diagram, here's my battery, which is 12 volts. Here's the light bulb. It says 40 watts. Alright, question is calculate the resistance. A 40-watt automobile headlight designed for 12 volts. So now the bulb has particular limitations. Especially for a motor vehicle, for cars and light vehicles like that, the battery is 12 volts, the standard voltages. Motorcycles, I think it's 6 volts probably. Big heavy vehicles, sometimes it's 24 volts. So you can't just replace whatever lights you want. You have to go with the right rating. You have to look for the right voltages. So this light bulb is designed for 12 volts. So it's directly connected to the battery, so the voltage across the light bulb is also 12. So if it outputs 40 joules per second, that's 40 watts, we can find the current in the circuit. We can use P equals VI, 40 equals 12 times current. So current is 40 divided by 12. 40 divided by 12, what is that? 3 point something. 40 divided by 12 is 3.33. Is the current. Then the question is, what's the resistance? Now the bulb has some resistance. We know that the voltage across this thing is 12, so we use V equals IR. 12 equals 3.33 times resistance. This gives us the resistance. 12 divided by 3.33 equals, what do we have? 12 divided by 3.6. So that's the resistance of this light bulb. Now, what I did was a two-step procedure. I found the current using watts using the power and then use Ohm's law. I can do this in one step as well. If you think about this equation, P equals, we are looking for the resistance, we have the voltage. So how about this one? V squared over R. 40 equals 12 squared over resistance. Resistance is 12 squared over 40. So let's try that. 12 squared over 40. I get the same answer, 3.6 ohms. Okay, so either way is fine. This second method is shorter, just one step if you remember the equation. Alright, okay, let's move on. Okay, another common household term or thing is that paying your electricity bill. Right? So when you use electricity company sends you a bill. Now, they have this particular, you might have noticed this particular term if you ever check your bill. It talks about something called kilowatt hours. Why is that? Now, that is how they charge you. If you look at this term, kilowatt hours, kWh, watt is power. Kilowatt, right, means 1000 watts. So if you use 1000 watts or 1 kilowatt, if you use 1000 watts for 1 hour, that amount of energy is called 1 kilowatt. So 1 watt is 1 joule per second, right? So what is 1000 watts? That is 1000 joules per second. That is 1 kilowatt. 1 kilowatt is 1000 joules per second. And let's say, for an example, in your home there is one appliance is working at the moment. It is a 1000 watt device, probably like a microwave oven. If you run it for 1 full hour, the amount of energy it's going to consume is going to be 1 kilowatt hour. So kilowatt hour is a joule measurement. Even though it has this kilowatt, this power portion in the front, power multiplied by time brings it back to energy, brings it back to joules. So what is 1 kilowatt hour? 1 kWh equals 1 kilowatt is 1000 watts times hour. So 1000 watts or 1000 joules per second. 1000 joules per second multiplied by 1 hour is 3600 seconds. The seconds cancels out, giving you 3600 and 3 more 0 joules. Or you can write this as 3.6 times 10 to the 6 joules. This is the amount of 1 kilowatt hour. And then they will charge some dollar amount for this amount of energy. Like, I'm not exactly sure about the current numbers, but typically I would say 1 kilowatt hour is about 15 cents. This many dollars. So if you had used 10 kilowatt hours, you will be paying $150, right? So like that, so now you have an idea based on the wattage of the different appliances you have at home, and based on how long you use them per day or per month, that's how the electricity bill adds up. Alright, so let's try some more examples. Okay, here's one. An electric heater draws a steady 15 ampere on a 120 volt line. How much power does it require and how much does it cost per month, 30 days, if it operates 3 hours per day and the electric company charges 9.2 cents per kilowatt hours? This book was written, these PowerPoints were made long time back, probably in 2009 or something. The numbers could be a little higher than that. It won't be 9.2 cents, maybe a little more than that. But let's see. current it draws is 15 amps. Voltage in the lines is 120 volts. How much power does it require? What's the power? Power is VI. So 120 times 15. What is 120 times 15? 1800. So for this electric heater, the power consumption is 1800 watts, means it uses 1800 joules every second. And how much does it cost per month if it operates 3 hours a day and the company charges this many cents per 1 kilowatt hour? Okay, so the summary of this question is, what's the total cost? If you use it for 30 days and 3 hours per day, what's the total cost? So the cost is based on the amount of joules you are using, right? 1 kilowatt hour is 3.6 10 to the 6 joules. So let's find out the total number of joules you are using, and let's see how many kilowatt hours are there in that. And each kilowatt hour is 9.2 cents. It sounds a little complicated, so we'll go step by step and figure out the total cost. Alright, what's the total energy you are using? Per day, it's 3 hours. So 3 hours means 1 hour is 3600 seconds multiplied by 3. So this many seconds per day. That's per day, so per month. It will be this number, 3600 times 3 times 30. So this many seconds per month we are using this. So the total energy per month, it's using 1800 joules per second for this many seconds, right? So that will be 1800, 3600, 3 times 30 joules. This is the total amount of joules we are using per month. So let's see what's that number is. You guys can do the math. I'm not gonna do all the math before I come to the last answer. And let me just calculate it. Easy for everybody. 1800 multiplied by 3600 multiplied by 90. The big number, 5832 times 1, 2, 3, 4, 5. 5 or 5.832 times 10 to the 8 joules. This many joules per month. We know that 1 kWh is 3.6 times 10 to the 6 joules. So how many kWh, how many kilowatt hours in this? Number of kilowatt hours per month. We divide this 5.8 by 3.6. So 5.832 divided by 3.6, 1.62 times 10 to the 2, 162 kilowatt hours. 162 kilowatt hours. Okay. All right. Then each kilowatt hour is 9.2 cents. So what's the total cost just for this one heater? So I'm gonna do it over here. Cost is 9.2 cents multiplied by 162. So whatever the answer you get is in cents, divided by 100 to make it dollars. So I get approximately $14.9 or $50, right? So just for this heater, if you use it 3 hours a day for 30 days, end up paying $15. So you can think about all these other appliances. If you run the microwave often, the refrigerator is always running, draws a lot of current, the washer, dryer, AC, heating, all that, so that adds up to your bill. But if you want to calculate, if you want to have an idea how things work, this is how you do the math, this is how they do the math to charge you for your electricity usage. Alright, let's move on, see what else we have. Alright, here's another example from nature. Lightning. There is much variability of lightning bolts, but a typical event can transfer 10 to the 9 joules of energy, about 20 coulombs of charge, across a potential difference of perhaps 10 to the 5 times 10 to the 7 volt. That's a huge voltage compared to the batteries that we've been talking about, 3 volts, 12 volts, like that. During a time interval of about 0.2 seconds, in a fraction of a second, this much energy, this many number of charges can be delivered. Use this information to estimate the current in the lightning bolt, the average power delivered over 0.2 seconds. Okay, so what do? Current is, we know that it's charge over time. In this case, 20 coulombs in 0.2 seconds. So about 100 coulombs per second, or 100 amperes. The average power delivered. Power. You can do power equals VI 5 times 10 to the 7, current 100. So 5 times 10 to the 9. This many watts. What is this? Kilowatts, megawatts. This is giga or gigawatts. 5GW. That's a lot. This much power. So a single lightning bolt delivers about 10 to the 9 joules, right? So this is the quantitative math part of it. But conceptually, think about it. If we can harness this energy for useful purpose, I mean, lightnings, you don't play with them, you don't go out and nest lightnings, but if we can come up with some kind of technology, I know there's a lot of studies going on, but so far, because of this massive amount of energy and voltage involved, it's really difficult and dangerous to harness this. But if somebody can figure it out, this many joules is about the average household electricity usage per month in one house. So one lightning can power a regular size house for a month. And around the world, lightnings happening all over the world. Every second there's lightnings going on somewhere on Earth. Imagine if you can harness all this. Half the world power needs will be just covered using these things. Alright, just a comparison. Okay, let's move on. Trying to keep the video short as well. So let's talk about electrical safety and how to properly use the power in household circuits. Now we'll get to this sometime later as well. The electricity that we use in our household circuits means, the electricity that comes out from these wall outlets. That's AC, alternating. AC, alternating. current. So a regular battery, that one we use this symbol, this is DC. A regular battery will give you a unidirectional current. If you connect this to a resistor, it always goes in one direction. This is DC. The voltage is DC, also the current is DC. Right? DC stands for direct current. The voltage is also DC. It always goes in one direction. Alternating current or alternating voltage, we just say AC voltage. The symbol is this, a circle with a wave-like sign in the middle. Now if you connect this to a resistor or something, the current goes this way in one instant, and the next instant it will change the direction and it will flow in the opposite direction. So most of the household appliances, this is not an issue. Let's say it's a heating element, like an electric heater. It doesn't matter which direction the current is flowing. As long as there is current, it's fine. If it is a light bulb, again, this is changing direction so fast, you won't see that it's going back and forth. If we can bring it down to a slower rate, like maybe like 5 Hertz or something, that it changes direction 5 times a second, you will be able to see the brightness increases, decreases, decreases back and forth. But in household circuits, it changes about at a rate of 60 Hertz, changes direction 60 times a second. The brightness changes in the light bulb. Every time it changes the direction, it drops to 0 and goes back to the highest value. So there's a little change, but our eyes are not that sensitive to see that. Certain devices, instruments need current to be in one direction, so there's converters inside to convert AC into DC. Okay, so let's see what this slide is about. The wires used in homes to carry electricity have very low resistance. It has to be low resistance, otherwise it's going to use up a lot of voltage. However, if the current is high enough, the power will increase and the wires can become hot enough to start a fire. Yes, most of the accidents in houses, fire accidents, are caused by electrical issues. So let's say there's a wire and goes to this light bulb over here. This is a power cord connected to the outlet. These wires have some resistance, right? And if you try to draw too much current, we can find the power using this equation, I squared R. If there's a lot of current in this, I squared increases, the wire itself is going to emit a lot of power as heat energy. It can heat up and then create problems. To avoid this, we use fuses or circuit breakers, which disconnect when the current goes above a predetermined value. So what is a fuse or a circuit breaker? It's a very essential safety device. Let's see how these things look like and what they do. Fuses are one-use items. One-time use. If they blow, the fuse is destroyed and must be replaced. So what's going on here? Let's say there's some appliance like a washing machine or something. Alright. So here's the power cord, goes to the wall outlet. Inside the circuitry there is this little fuse thingy. So the current comes in, goes through the fuse and then goes to the motor and rest of the electronics. If the machine is gonna draw too much power, too much electricity, it can be dangerous, it can burn these connecting wires, but before that the fuse will take care of it. So it's this little cylindrical thing. So the current comes in, current comes out. Inside there is a very thin wire. we call it the fuse ribbon. So when there's too much current, if the current is above some standard number, this thing heats up and it melts, so it breaks the connection. So that's a safety thing. So after that, there won't be any current in the circuit, right? If there's a leak or something, let's say somebody comes in, try to operate this, there is a leak in the circuitry, and so there's electricity present on the casing. You go and touch this, you are creating, if your hands are wet and if your feet also wet, can happen when you're working with washing clothes and all that, you are creating a secondary path through you to the ground. So the system is going to draw too much current. This is bad for the person. First of all, it's really bad, and it can create fire also. Before any of that happens, a good machine will have a fuse that can disconnect the circuit. Same thing inside the distribution panel. There are fuses, there are circuit breakers will go off before a large current flows through the machine or to the person, right? I'm just adding some stuff, like that's some safety advice here. Sometimes, not everybody, but some people, because they are lazy to go to the hardware store and buy a fuse, once the fuse blows up, they'll replace this wire with some piece of wire they can find around the house. That's not a good idea, because accidentally, if you put something thicker than it should be, a thicker wire, right, even if there's a large current, this wire can withstand that. It won't melt. That's really bad. So the fuse is supposed to break the circuit, and that won't happen, and that's really bad. So the best thing to do is, if a fuse is bad, just replace it with the right rated recommended fuse. Alright, moving on. These are circuit breakers. They're called bimetallic circuit breakers. So there's a very interesting mechanism. There's a metal strip that current goes through that, and in case if there's too much current going through this, more than the rated amount, this particular metal strip contains two types of metal. They have different expansion rates, so they expand differently with heat. So because of that difference, when it expands, it bends. That bending can break the connection, and that's how you prevent dangerous currents in the circuit. So it's a particular type. There are different types. This particular one has a bimetallic strip, like a combination of two different metals. Two different metals to have two uneven expansion so that it bends. Okay. So these are certain things that you should read more on your textbook to get a better idea, for background information. Good for conceptual questions, potential conceptual questions. So make sure to read more about how these things work. You can also Google. Alright, moving on. Power in household circuit. Will a fuse blow? So, determine the total current drawn by all the devices in the circuit shown. Okay. You have a light bulb with 100 watts, heater 1800 watts, 350 watts, hair dryer with 1200 watts, all connected parallel to this power line, which has 120 volts. So from the electrical company. Electrical company provides 120 volts. Inside the house, there's various outlets, so you plug different things. So the question is, will a fuse blow? How do you figure that out? Why do people say, your parents and elders, they tell you don't plug too many things into a single outlet? Why is that? Because when you plug multiple things into a single outlet, let's say there's a wall outlet, there's only two sockets, but you plug in a power strip kind of thing with multiple outlets, and then you can plug multiple things into that, and then you run all of them at the same time. Let's say the TV, the computer, the hair dryer, the heater, everything at the same time. What happens is all these wattage going to add up. So the total wattage is what? In this case, 100 plus 1800 plus 350 plus 1200. So 1800, 2000, 3000, 3450 W, I think, total. So the total power is 3450 watts. How much current this going to draw? We know that P equals VI. So 3450 is 120 times I. So I equals the current in the circuit almost 29. So I have 28.75 amps. So if you connect all this, everything into one outlet, like outlets right next to each other, and turn all of them on at the same time, these lines over here, they're going to draw 28 amperes, 29 amperes through them. Household circuitry, the wires are normally designed for 20 amps throughout the house. Only exception is the special connections for washer dryer, actually for the dryer. Other than that, rest of the household is wires are designed for this. So you are drawing more than that. The fuse should go off before it overloads. If that doesn't happen, the circuit breakers, if they don't function well, then eventually this can catch fire. Alright, so the best thing is to separate them at different outlets. Maybe take the electric heater off and put it in another room or something like that, or don't run them at the same time. Okay, moving on. Okay, here's another question. Let's clear this. Your 1800 watt portable electric heater is too far from your desk to warm your feet. Its cord is too short, so you plug it into an extension cord rated at 11 amps. Why is this dangerous? Something we always do. If the wire is too short, we plug it to an extension cord. From now on, you know whether to use that extension cord or not. Especially if you are running it overnight, it can be a little dangerous. So power is 1800 watts. What's the current? P equals VI, current equals P over V, 1800 over 120. Uh, 15 amps. So this thing is going to draw 15 amps. You connect it to a extension cord rated for 11 amperes. 11 amperes is good to run like a light bulb, a TV, or a music setup, small items, not these electrical heaters. So 11 amperes, you are drawing 15 amperes over that, too much for the cord. Eventually it can melt and even catch fire. Okay, so what do? Either you move yourself towards the electric heater or get a bigger extension cord rated for 20 amps or so. Right. Okay, so next thing we're going to discuss is alternating current. We'll come to that in the next video. So as of now, electric power and how to calculate the power usage, how to calculate the cost of using electricity. Those are the topics that we cover in this video, and how to use electricity safely at home. Things like not to touch electricity with wet hands, Wear insulated shoes when dealing with electricity, like rubber slippers, rubber shoes that are dry. They shouldn't be wet. Don't touch them directly if they're exposed, and if you're not sure about it, don't touch them directly. Electrical repairs, if you are not trained to do that, don't do it. Get a trained person to do that. Circuit breakers, electric fuses and all that should be monitored and replaced when necessary with proper replacement. And yep, that's kind of the summary of this chapter. Thank you everyone. All right then.